So I'm going to talk about the work energy theorem. So the work energy theorem is the same theorem as that we talked about in class before, but now we're just adding in a second type of energy. So now we have elastic potential energy that we can also have. So our energy before is still equal to our energy after, but we can also have elastic potential energy along with gravitational and kinetic. So if I might have gravitational potential energy, I might have kinetic energy, and I might have elastic potential energy. That would all equal those same types of energy after. So the combination of those energies would all be equal to each other. So this could be related easily to a rubber band. So if I start with a rubber band, the rubber band right now has 0 energy. So in order for me to give it energy, I have to do work to it. So I have to apply a force over a distance. So I can do that by just stretching my rubber band. So if I have a rubber band, I do work to stretch the rubber band. To give it energy. Once the rubber band is stretched, so if it's now stretched, so it's now stretched some distance here. So the energy it has right here is elastic potential. Now once I release that rubber band, so if this rubber band stretched and I now release it, that elastic potential right away will turn into kinetic here. And then as it goes up, that kinetic energy is turning into gravitational potential energy. And if it's shot straight up, at the very top, it would have gravitational potential energy. And what I could do is I could set the energy at any 2 of these points equal to each other. So I could set the elastic potential energy here to the gravitational potential energy if I shot this rubber band up to figure out what is the total height it reaches. So what we're going to do is we're going to look at a conservation of energy problem with this. So if I have a 1.1 kilogram mass that's suspended on a vertical spring who has a spring constant of 120 newtons per meter, we want to figure out how much it stretches by length. So from this, I know that it's 1.1 kilograms. So if I think about that mass, it has gravity going down, which is roughly 11 newtons, and I have my Fs going up. So because this is motionless, I know that these two are equal to each other. So my Fs is 1.1 newtons. So to solve for this, I can set Fs equal to Kx. So I have my Fs is 11 newtons. I have my spring constant is 120 newtons per meter. And then I can figure out what is my spring constant, or my x. So when I solve for this, I figure out that my x is 0.09 meters. So I know that if I have a spring, so I have my spring right here, and I'm adding a mass onto my spring is going to stretch that distance. So it's stretching 9 centimeters. So now for the second part of this question is the object is going to be pulled straight down an additional 20 centimeters. So if we think about what's going on here, I have this spring. So this spring was originally this length. So what I did is I added a mass onto it, and adding that mass onto it stretched my spring in a 0.09 meters. Now what I'm going to do is I'm going to pull this down more, so it's going to stretch it farther, and it's going to stretch it in another 20 centimeters, so 0.2 meters. So from its rest position, this is stretched 29 centimeters. So when we do this type of problem, we're trying to figure out what is the speed as it passes through its original position. So we're trying to figure out what is the velocity from the position when it was already stretched. So what is the velocity here when it reaches this position? At that position right here. So to do this, what we're going to use is conservation of energy. So to do this, I'm just going to show you guys what's going on here. So I have my spring, and I'm gonna add a smaller mass to my spring. So I add a mass to my spring. And my mass, so we're just gonna look. So it's starting at this position. It's now you're seeing that it's stretching to here. So this is where it's stretching to. So now I'm gonna pull it down an additional distance. And then when I let go, you'll see that as it passes by this position here, it has a speed and it's going up farther than that. So thinking about that, you want to think about that when you think about using conservation of energy. So what we want to do is we want to look at what kind of energy does it have at two different positions. So what I'm going to do is I'm going to look at it from this bottom position here to this position here. So at this bottom position, this is where that spring is totally stretched out. So in this bottom position, so I'm going to call this my energy before, all of my energy here is, it's not moving, so I don't have kinetic. It doesn't have a height, so I don't have gravitational potential, but the spring is stretched. So that means I have elastic potential. Now when it passes through this position here, I'm going to see that so my energy after, it's moving, because I'm trying to find my velocity, so it has kinetic. It also is stretched some, right? So because it's stretched some, I also have elastic potential. And I'm also off the ground. So because I'm off the ground, I also have gravitational potential. And now what I'm going to do is I'm going to set all of those energies equal to each other. So I'm going to set my energy before equal to my energy after. So my energy before is elastic potential. And that's equal to my elastic potential in my second spot, plus my kinetic, plus my gravitational potential. So I'm going to have 1/2 times my K, which we had from before, so 120, times my X. So this is how much is the spring stretched in this position here. So it was originally stretched 9 centimeters, and then it stretched 20 more centimeters. So my total stretch in this position here is 29 centimeters, so 0.29 meters. And that'll be equal to my elastic potential in this position, so that's 1/2 times 120 times the distance it's stretched there. So it's stretched here 0.09 meters, and then plus 1/2 mv squared for, so my mass for this was 1.1 meters, right? So 1.1 meters, 1.1 kilograms, kilograms, and then times velocity squared, plus my elastic potential. So my elastic potential is 1/2 times my spring constant, 120. Oh wait, no, we already did that. My gravitational potential. So plus my gravitational potential. So my gravitational potential is mass times gravity times height. So I'm going to have 1.1 times gravity, so I'm going to say 10, times my height. Now my height is based off the ground, so if I look, it's from these two positions here, so my height is 0.2 meters. So now I'll just do some algebra to solve for this, and if I do my algebra to solve for this, this will give me a velocity of 2.07 meters per second. Okay, so when we do conservation of energy problems involving springs, you also have to just think about what types of energies you have. So we're just adding a second or a third type of energy on to our mechanical energies.